For a typical univariate CDF, capital Fx, we know a property of the graph that as x goes to infinity, the graph will approach 1. And as x will approach minus infinity, the graph will approach 0. The analog of these two limits in the case of a bivariate CDF is as minimum of x and y goes to infinity, fxy equals 1, and as the minimum goes to minus infinity, then this limit is equal to 0. I should actually write tends to. Now notice the subtlety of the statement. When I am working in R, I can understand going towards infinity is going towards right and going towards minus infinity is going towards left. But when I am in the plane, what is meant by something goes towards infinity? I can go like this, I can go like this. Are all these things going towards infinity? No. I say minimum of x and y going towards infinity, which means both x and y are going to infinity. When I am going towards minus infinity, the meaning changes. I am still using mean, not max, but the meaning changes because now it says if at least one of them is going to minus infinity, then this condition will be triggered. Here, both of them must go to infinity. Here, at least one of them has to go to infinity. Thus, for these three arrows, this is going towards infinity, minimum goes towards infinity. In this case, the minimum is going to minus infinity because I am coming down. This one is also going to minus infinity because I am going towards the left. If I go vertically up, in that case, I am in neither this situation nor in that situation because the minimum is staying fixed and it is not going towards minus infinity also. Let's try to prove one. I have written down this statement in terms of mathematical logic. I am working with a limit, so fxy has to go towards 1. So I am doing fxy greater than 1 minus epsilon. Remember, fxy is always less than 1. So I mean less than or equal to 1. So fxy greater than 1 minus epsilon guarantees that fxy is close enough to 1. So whatever epsilon you choose, there will be some capital M such that whatever xy you take, if minimum of xy is greater than m, then fxy is close enough to 1. So first you have to digest this statement and understand that this is same as that. You start by taking any epsilon positive. The main idea behind the proof is that if you are considering capital F at xy, in that case you are considering the probability of this infinite rectangle, and as xy goes towards, I mean the minimum of xy goes towards infinity, this rectangle is going to cover the entire plane, so the probability must go towards 1. But we have to be careful here because xy, they can take uncountably infinitely many values, and our continuity of probability theorem works with only countable things. So instead of working with all x comma y, we are working with just n comma n and taking this nn. So this also is a sequence going towards infinity, that is their minimum is going towards infinity, but now we have a countable collection. Then n's obviously increase to the entire space omega. Here omega is where the random variables x and y are defined. So by the continuity of probability result, I have this. Because it is countable, now I can use the continuity of probability. And so f n comma n, that limit is equal to 1. So from this condition, I can get a capital M in natural number such that f mm is close enough to 1. Now I was proceeding down this line, I had already taken epsilon, I am now choosing m, I will choose this particular m. Now my proof has come up to this, so I will now take xy. Take any xy with minimum of xy greater than m. My duty is to now show this. Now this fxy has to be greater than or equal to fmy. Why? Because minimum of x and y greater than m, that means x is also greater than m. So x is greater than m and y remains fixed. So by non-decreasing property, this must be greater than or equal to this. Again similar argument, y is also greater than m. So by the non-decreasing property with respect to the second argument, I get this. But fm is already greater than 1 minus epsilon, and that proves this thing. So completing the proof of 1. Now 2 of course can be proved in a similar fashion. One important property for univariate CDFs was its right continuity, which pictorially meant whenever there is a break, the dot is connected to the right hand end, and mathematically it meant when x goes to a plus like this, then the limit will be equal to fa. Now in case of bivariate or multivariate thing, there is no clear left or right direction because we are working in the plane. So we have to replace it by what I call northeast continuous. So if you take a point here and you let it approach it from the northeast side, then the limit will match the value. So you cannot approach from this and guarantee that the value will match. I start with fxy, join CDF of xy, and I take any arbitrary point AB. Now I take a sequence of points xn, yn that comes down to AB in the sense xn decreases to A, yn decreases to B. Then f of xn will really go to f of AB. The idea of the proof is you are considering f of AB, which means the probability of this infinite rectangle, and your xn, yn is somewhere here approaching from the northeast side. So f of xn, yn will be the probability of the bigger rectangle. Naturally, as it comes down, this sliver will go to 0. I define these two things appropriately. Now it is easy to see that ans will decrease to a, that is if I take intersection of all ans, in that case we have this. So by continuity of probability, I have this. This is nothing but this, and this is nothing but that. Hence, fx and yn goes to fab as required. Now this is essentially the same format as the last theorem. I have any arbitrary AB, but now xn increases to A and yn increases to B. I still am working with the same an and A. My question is this statement true or false? Ans now increase to, because I made them increase to A or not?